Every engine, star, and living cell is bound by a single cosmic rule. Space, time, and probability demand that order inevitably decays into chaos. This is the second law of thermodynamics. It dictates that time only moves in one direction. During the 19th century, engineers were trying to optimize steam locomotives. Physicists like Rudolf Clausius realized that a perfect machine, one that converts heat into work with absolute efficiency, is physically impossible. Some energy is always lost. Clausius gave this inevitable loss a mathematical metric, entropy. In simple terms, entropy measures a system's unavailable energy. It's the degraded, low-grade thermal heat that you can no longer harness to push a piston or turn a wheel. And Clausius proved that in any real-world process, total entropy must always increase. Later, Ludwig Boltzmann connected this microscopic loss to atomic probability. He showed that entropy isn't some invisible fluid. It's simply the realization that there are an astronomical number of ways for atoms to be scattered and disorganized, and almost zero ways for them to spontaneously arrange themselves neatly. Because chaos is overwhelmingly probable, the universe is locked into a steady march toward what physicists call heat death. Eventually, all temperature differences will be erased, energy will be completely uniform, and physical work will become impossible. Infinite energy is off the table. Or at least, that's what the math demanded. But in 1867, a Scottish physicist named James Clerk Maxwell designed a thought experiment that cleanly bypassed the laws of probability. This animation shows the setup. It's an isolated box filled with a completely uniform gas. Now, uniform temperature is just an aggregate average. Down at the atomic scale, the gas is actually a chaotic mix of fast-moving hot molecules, marked in red, and sluggish cold molecules, marked in blue. Maxwell introduced a hypothetical, microscopic, hyperintelligent entity standing at a partition in the middle of this box. This is Maxwell's demon. It tracks every molecule's speed. When a hot red particle approaches from the left, the demon opens a tiny frictionless door to let it pass. When a cold blue particle approaches from the right, it lets it slip to the left. The demon doesn't push the atoms. It doesn't consume fuel. It simply opens and closes a massless door. Yet through pure observation, all the fast molecules end up on the right side, meaning it gets hot. All the slow molecules get trapped on the left, so its temperature drops. A perfectly mixed gas has spontaneously separated into two distinct zones. The demon has taken a high entropy state and organized it into a low entropy state, entirely for free. If you connected a heat engine between those two zones, you could extract endless electricity from background room temperature. If this entity could exist, the second law of thermodynamics is broken. For decades, physicists scrambled to find the missing variable that would defeat the demon. Early attempts argued the demon would need to shine a tiny light to see the molecules, and the heat from that microscopic flashlight would produce more entropy than the sorting process destroys. But that assumed a specific, clumsy method of observation. The true resolution didn't arrive until 1929, when Hungarian physicist Leo Szilard stripped the chaotic gas box down to its bare mathematical essentials. We are looking at a diagram of the Szilard engine. Instead of billions of atoms, Szilard placed a single lone gas molecule inside a cylinder. The demon drops a partition down the middle. As the single molecule bounces around, it exerts kinetic pressure against the partition, pushing it outward and successfully doing mechanical work, like lifting a microscopic weight. But the engine only extracts energy if the demon hooks the pulley to the correct side. It has to know exactly where the molecule is trapped. The entire expansion relies entirely on a single bit of binary data, a choice between left or right, 0 or 1. Szilard proved that the information itself makes the physical work possible. Acquiring that bit of data carries a literal, mathematically defined thermodynamic cost.
Knowledge is a physical reality, bound by the exact same conservation rules as coal. Finding the exact moment that cost is paid took another 30 years. In the early 1960s, researchers at IBM tried to determine the absolute minimum amount of heat a microchip had to dissipate to execute logical operations. A physicist named Rolf Landauer analyzed standard processing gates like AND and OR. He found that you can move data around or run calculations reversibly without actually requiring the hardware to dissipate heat. The math allows most computing to be thermodynamically free, except for one specific action. This animation illustrates what happens during memory erasure. When a computer deletes a bit of data to reset a register, it forces two possible previous states, a 1 or a 0, into a single uniform state. Landauer showed that reducing this logical variance inevitably compresses the physical phase space of the hardware. That lost information has to go somewhere, so it is expelled from the machine as thermal heat. Apply this erasure principle to our microscopic gatekeeper. The daemon doesn't have an infinite hard drive. As thousands of molecules fly toward the partition, it logs their positions until its internal memory is completely full. To keep operating the door, it must clear space. It has to overwrite its previous measurements. The thermodynamic debt isn't owed when the daemon observes the gas or opens the door. The entropy removed from the container is violently dumped back into the universe the precise microsecond it deletes its memory. The cosmic ledger balances. For over a century, Maxwell's gatekeeper was just a theoretical debate. The energy footprint of a single bit of data was too small for classical instruments to measure. But modern nanotechnology and optical trapping systems have finally allowed experimental physicists to build functional daemons in the laboratory. This video shows an optical tweezers experiment. That single glowing silica bead is suspended in fluid. Ambient heat from the surrounding water molecules causes it to undergo violent Brownian motion, randomly vibrating back and forth inside the microscopic well. A high-speed camera watches the bead with nanometer precision. The moment the camera records that the bead has drifted to the far left side of the well, an automated script drops an electronic barrier down the middle, trapping it. With the bead locked on the left, it tries to bounce back toward the center. As it hits the new electronic wall, it physically pushes against it. By slowly moving the barrier, the lab equipment extracts tiny amounts of mechanical work out of the background heat of the liquid. The lab results matched Szilard's mathematical predictions perfectly. The simple knowledge of where the bead randomly landed was directly converted into measurable physical power. The Landauer erasure limit represents a concrete barrier for the global semiconductor industry. Every time a processor deletes one of its billions of bits, it dumps a fixed amount of heat into the hardware, a cumulative thermal burden that chokes the speed of modern microchips. This diagram shows a potential solution: reversible computing architectures. These circuits are designed so that logic gates never terminate or combine data lines. By ensuring inputs can be reconstructed from outputs, the chip avoids erasure entirely, functioning below classical thermodynamic limits. Maxwell's daemon proved that the conservation laws governing steam engines also apply to the digital bits in our processors. This adds a third physical parameter to the thermodynamic ledger alongside matter and energy, information. Because data carries a physical mass-energy footprint, every arrangement of atoms represents a specific piece of data. We can manipulate the physical world with bits, only because the landscape itself is an information architecture. From the sorting of gas molecules to the logic of a microchip, the universe operates as a single, unified bookkeeping system, where the simple act of forgetting requires a permanent payment of energy.